Alright class, this is the last video. Divergence theorem part 2. We're going to do example 4 here. Find the net outward flux of this field. X in the I direction, well, x over rho cubed plus y over rho cubed plus z over rho cubed. And where rho is defined as that, across the boundary of the region. So, first thing we have to do is find the divergence. But this is a little bit more tricky with derivatives. We're going to actually have to use chain rule here because it's kind of implicit. Because rho is also in terms of x, y, and z. So the first thing I'm going to do is I'm going to take the derivative of this with respect to those letters, and I'm going to say, well, the derivative of f with respect to x, and I'm going to do the quotient rule. And since rho has x's in them, we have to treat that as a variable. So if I do low d high, and again I'm only doing the I direction right here, so we can ignore the j and the k. So low would be rho cubed d high, which is x with respect to x, which again is 1, minus the high, which is x, d low. The derivative of this is 3 rho squared, but then, because this is also not just in terms of x, we have to then include d rho dx. So I'm going to have to find that later. We'll deal with that in a second. All over the bottom squared, which is rho to the 6th. So the problem here is we don't know this yet. Okay? And so we can do that over here though, because we know that rho is equal to x squared plus y squared plus z squared to the 1/2. So if I take this with respect to x and leave y constant and z constant, I get the derivative of rho with respect to x is 1/2 times all of this. Now that's just to the negative 1/2, which means it's just on the bottom, and then times the derivative of the inside, which is 2x. So if you simplify this, the 1/2 and the 2 cancel, and then this all goes below, so you get x over all of this. Well, all of this to the 1/2 is defined as rho, so we can put rho back in there. Okay? So now I go back over here and I get that the derivative with respect to x is rho cubed minus x times 3 rho squared times x over rho. Okay? And then we get that all over rho to the 6th. So we end up with rho cubed minus 3x squared rho over rho to the 6th. Okay? So that is df dx. Now, if you do that with df dy, the only difference is you're going to have a y here, and then when you do d rho dy, same thing, you're going to get y over p. So I'm going to just write that over here. D rho dy is y over rho, I should say. And then same thing for d rho dz, dz over rho. Okay. So that means that when you do the other two parts for the divergence, so now we can find the divergence, because it's basically the same thing 3 times. The divergence of f is equal to df dx, which we have here, rho cubed minus 3x squared rho over rho 6th, plus, and then it's going to be the same thing but with y. If we would have done the same process, and then same thing with when we do df dx, or sorry, df dz, we would get the same thing but with z. Okay, so I haven't done the integral yet. I have to put these all together. First thing we notice is we get this plus this plus this is 3 rho cubed. Now, do you guys see how there's a minus 3 for each of these? I'm going to factor a minus 3 out, and I'm left with the x squared plus y squared plus z squared. Well, again, when you go back up to the top, x squared plus y squared plus z squared is actually equal to rho squared. And then we also still have another rho attached to that. So what do you guys see? Hopefully you guys see that on top you get 3 rho cubed minus 3 rho cubed, which means that the divergence of f is equal to 0, which means, therefore, that the triple integral over the domain of the divergence of f equals 0. And what does that mean? In this example, that means that at any given point, or I guess for the whole thing, the flux entering will balance out and always equal the flux exiting the region. I can't write. Okay, so that's all we have to do for that problem. It was a little weird with derivatives because we had another variable in there, but using implicit differentiation and substitutions, we were able to figure out our divergence, and it was 0, so that we don't even have to integrate, which is nice. The flux is 0, which means the flux entering is equal to the flux exiting. Okay, so now really the last thing on this note sheet is a recap. So I'm going, again, you could pause if you need to write all this problem down, but I'm going to go down to the bottom. And this is basically summarizing the last two the big ideas of flux and circulation using these new theorems. Okay, first of all, flux. Remember, Green's theorem had both flux and circulation. When we were in 2D, we used both. There was the two different setups. Okay, there was another form for it too, by the way, on the Green's theorem. We had the mdy, ndx, and that, but these are the general forms. So to find circulation, you can use the tangent form of Green's theorem. And if you need to find flux, the normal form. Notice how the normal form uses the divergence, the gradient dotted with f, and then even the divergence theorem uses the same thing. The only difference is this is 2D versus 3D. This is the area of the curve that's in 2D. This is the volume of the region in 3D. That's the only difference here. And I hope you guys noticed that when we were doing the problem. We still found the divergence and did the integral. For circulation, Green's theorem and Stokes' theorem is the same. Remember, for Green's theorem, we only ended up with the k component of the curl because, again, we were in 2D on x and y plane. So we only had the k component of the curl, which is the del cross f, and then we integrated over the shadow, or the region that the curve was in. So then, with Stokes' theorem, it could be any surface that's in 3 dimensions. So now instead of k, there's a normal unit vector, which incorporates x, y, and z. And so that's why that's now popping up there. And then instead of dA, because it's flat, it's the surface integral, or the differential. So we have to find it over the surface. So they're very similar formulas. We basically did the same thing. It just was more complex when we got to this chapter because we were in 3 dimensions. So there was a lot more pieces to deal with the surfaces. So yeah, you guys can pause the screen to finish writing these down, but this is a great just summary of what we turned each of the integrals into to find flux and circulation. And that's a wrap on the videos, guys. So the rest of the year we're going to be just doing some problems here and there. So if you have any questions, please email me.